Hi everyone, Happy New Year. Welcome to APCTP string seminar. Let me introduce today's speaker, Anurag Kaushal from TIFR India. Today he will talk about the bulk geometry and the target space entanglement. Please join me in welcoming our speaker, Anurag Kaushal.
Thank you so much for inviting me and giving me the opportunity to present a seminar at APCTP. So I'll talk about bulk geometry and target space entanglement. First of all, please feel free to ask questions if you have any at any point of time. So it's based on the following two sets of work. One which came out in 2020, and the other one which was published last year in 21. It's done in collaboration with Sumit, Gautam Mandal Sandip Trivedi, as well as Sinong Liu in the second paper. So Sumit is a faculty at Kentucky and Sinong was a student. Gautam and Sandeep are faculty here at TIFR. So this is the overview of my talk. I will begin with providing some motivation for why we are doing what we are doing. And then I'll talk about D-brane holography, which is really the arena or playground where we propose and test and do our thought experiments. Then I'll talk about target space entanglement, which is sort of the main theme of this talk. I'll spend quite some time on this. Then I'll go on and talk about entanglement in the bulk geometry, always restricting to this particular example of D-brane holography. Then I'll give a boundary proposal for bulk entanglement. I will also talk about a gauge-invariant definition of target space entanglement if I have time. And then I'll finally conclude with a summary. Okay, let's begin. So there has been this idea, a recent idea proposed by Ramstorm, Single independently, and by many other people, is that the spacetime, the gravitational spacetime, can emerge from quantum entanglement. In other words, it is entanglement that somehow holds the fabric of spacetime together. And there has been an increasing amount of evidence for this from EDSCFT. And the main point, the main key ingredient is the RT formula, which is basically says that within ADS-CFT, if you have a boundary region in CFT and you ask what is the entanglement of that region, then the answer is given by the Ryu-Taki energy formula in terms of the area of extremal surfaces going inside into the bulk. So in particular, this work of Ramstorm relies heavily on the RT formula. He was considering a situation which is very similar to the eternal black hole, which is dual to thermophile double of two CFTs. So normally, if the two CFTs are not interacting, the corresponding bulk geometries should be independent and have nothing to do with each other. However, if there is entanglement, the geometry is connected. And what Ramstorm showed was that if you turn down the geometry by turn down the entanglement, what happens is that the geometry collapses and separates into two parts corresponding to two different CFTs. And this was roughly his style of argument. And this was this hinted to the fact that it is indeed quantum entanglement that somehow gives rise to space-time. Now we can ask this question, but what happens if the boundary theory is just quantum mechanics? In particular, it doesn't have any spatial directions. Then, strictly speaking, one cannot really apply the RT formula, because then this boundary, it won't be a plane as I've drawn it, but it'll just be a point. In that question, and then there are examples of holography, for example, a D0-brane holography, which one should really think of, a close cousin of ABS-CFT, where you have a bulk geometry and a boundary theory, which is dual to it, but it's just quantum mechanics. So the question we ask is that, let's suppose that this idea is correct and there is some truth to it, that the space-time somehow indeed emerges from an entanglement. The question is, what is that entanglement in the quantum mechanics theory? So this is broadly the question that allowed us, that led to this work. Let me go on. So one can ask how to define entanglement in a theory of dynamical gravity. And the problem here is that if the geometry is evolving and the metric is changing, then it's not clear how to define regions, because as the metric fluctuates, you don't know how to define regions. However, for a smooth space-time geometry with approximate locality, what I have in mind is that you take G Newton tending to 0, such that you have almost classical geometry, and you can ignore the back reaction of the fields because G Newton is small. It is possible to define regions because geometry is essentially fixed. It's more like quantum fields in curved space with the space-time is background fixed. In that case, in this particular limit, or semi-classical limit, the entanglement then, if you define a region, is given by the entanglement of quantum fields, including the gravitons, which are sort of moving on this background. And we know that for quantum fields, the entanglement diverges. In particular, the leading divergence is an area law. So what, based on what many people have already suggested, so motivated by this area law and the Bekenstein-Hawking entropy formula, we expect that in a UV finite theory of gravity, this is important, that the entropy or the entanglement entropy be finite and not diverge. In particular, the role, the cutoff should be replaced by some parameter in the theory. And as has been suggested by many people, and we also propose that the cutoff should really be replaced by the Newton's constant. So there are various arguments given by various people, by Susskind and Uglum, who argue that this divergence renormalizes the Newton's constant such that area by G Newton remains finite. In particular, there's a very interesting paper by Jacobson in which, starting from thermodynamics, basically D equal to TdA, dq equal to TdS, he's able to derive Einstein's equation, provided that the entropy across any horizon, any Rindler horizon, not black hole horizon, is given by area by G Newton. So there are many arguments and hints why in a UV finite theory of gravity, the cutoff should really be replaced by G Newton. So in this talk and in our work, we asked the question that, let's say you choose a region in the bulk, and the entanglement entropy across that region in the bulk region is given by area by G Newton. We ask, what is the boundary quantity which reproduces this? And we remember we were focusing on D0-brane holography, where the boundary theory is quantum mechanics. So it's not clear immediately what is the boundary quantity which will give you this answer.
Hello, I just have a question. Can I interrupt?
Sure. Go
on. So Anurag, when you say you have a D0-brane holography and the boundary, you perceive it as quantum mechanics, but then we already know that the Alice-Bob thing in quantum mechanics. I mean, we all know this. So what is more that you're seeing here, or can you draw any parallel there? I mean, I'm a bit confused when you say it's quantum mechanics, because entanglement quantum mechanics is pretty well established. But I think when you say here, there's something more to do with strings, perhaps, right?
Yeah. So
what is that? Yeah, that is what I'm not able to see here.
Yeah, it will become clear when I talk. So if your question is specifically about the D0-brane holography, then it'll become clear when I come to that. But in general, so for example, let's say you're in flat space and there is no gravity. It's a Minkowski space. And you can choose a region and ask what is the entanglement of quantum fields in that region. And that has an answer. And that is well known.
Yeah, that is well known. You just divide, you just like, Hilbert space standard thing, right?
Yes, yes. And what we are proposing that it should also be true with very, weak gravity, in particular this limit. So that's very close to all, the background is fixed. And so it makes sense that the entanglement still has the same behavior. So there is some background and there are fields riding on that background. And that background for when it's a flat space, that it follows this answer. And we propose that it's true even in presence of very weak gravity. Does that answer your question?
I see. Okay. Yeah, but I thought maybe there's something more when something more to do with strings. Okay. Okay, let it be.
We'll come to that. We'll come to
okay.
strings.
Okay. Yeah. Okay.
Thank you for asking that question.
Yeah.
So before I proceed, I'll just flash the key results of our work, which is firstly, we give a precise definition of entanglement in the boundary quantum mechanics theory, and we call it target space entanglement. And we propose that target space entanglement is related to the bulk entanglement, which I just showed you in the last slide. And in particular, in the limit of smooth classical geometry, G neutral going to 0, the background is almost fixed. We propose that the entanglement in the bulk is given by the Bekenstein-Hawking formula. And the target space entanglement in the boundary theory should reproduce this answer. That's a proposal. There is some motivation for proposing this. There are some examples where this is true, but in general, it's not known, and we would like to test this and find whether this is really true. Okay, so I'll go ahead and, or maybe I can stop and take a few questions if you have any. Okay, I'll proceed.
Yes,
okay.
Go ahead.
So let me just mention briefly about D-brane holography. So basically, it's, as I said, you should think of it as a cousin of EDS-CFT, a slightly different cousin, because the bulk theory, the gravity theory, is not necessarily asymptotically ADS, and the boundary theory is not necessarily CFT in this holography.
Here, when you say D-brane holography, is it the BFSS model or?
It's very similar to that. You'll see. So BFSS model is a particular example. It's related to D-brane quantum mechanics. It's specific, but D-brane is something that comes from string theory.
Okay.
Yeah.
Right.
Type 2 is string theory. Yeah. So if you have a large number of D-branes, n, they self-gravitate and lead to a following geometry, which is given by this metric. And this D-brane holography was proposed in this paper. You'll at least recognize one name. So this is some metric. It has a dilaton, which is given in terms of this function, the harmonic function. Little r is the radial coordinate. Capital R is a parameter comes from the string. So from this full string theory, G is the string coupling, Ls is the string length, and so on. The one thing to note about this is that this description, this metric, the background described with this metric, is only applicable within a finite range. So in particular, if the radius becomes too small, the dilaton becomes large and the M theory takes over. If the radius is large, or equivalently energy is large, because energy is proportional to the radius, it's the same as in standard ADS. When the energy is large, you need to work with the full type 2 superstring theory and supergravity description theory. But however, if you make n very large, you can make this range very large, and there's a very large region where you have a supergravity description. The boundary, the dual theory, is given by this quantum mechanics theory, given by this action. So this theory, the main object are these n cross n matrix, Hermitian matrices, xi. There are 9 of them, and 9 because they correspond to the 9 spatial directions in the corresponding in the dual theory. So maybe I did mention this, that this is a geometry in 10 dimensions. So there are 9 spatial dimensions, and there are 9 Hermitian matrices roughly corresponding to the 9 spatial dimensions. So this theory is actually a gauge theory, and the action is invariant, as one can verify. Also, it's a supersymmetric theory, and there are fermions which I have ignored, and I will ignore further. It's not really. And this theory has a single scale, which we call lambda. It's given by this, and it's very similar to what any gauge theory like Yang Mills theory, where you can rescale your fields and there's only one coupling which sits outside the action. It's like that. So this scale is like that. So like ADS-CFT, this is a strong weak duality. So when the gravity is weakly coupled, which is the region we are interested in, the quantum mechanics is strongly coupled, and that happens at low energies. Again, like Yang Mills or QCD in 3+1 dimensions, at low energies become strongly. One particular interesting result that can, that's a check that this is a duality, is that there's a velocity dependent potential experienced by a probe beam in the supergravity. So I showed you the metric. Imagine that there's a probe zero brane moving in that metric. It experiences a potential or a force, which is velocity dependent. And you can derive that same potential from the quantum mechanics theory using some effective action calculation. So it's one, there are other checks of this duality, but this is one, important and one of the first checks of this duality.
So can you let me know the difference between this model and the BFSS model? What? It's very similar, but
it's very similar, yeah. So it's like, so all these models actually come from, so starting from the string theory, you take different limits. And so you take one particular limit and you come to this model. You take a slightly different limit and you come to the BFSS model. So they are related. The parent theory is the same, which is this 10-dimensional superstring theory. But it's like they are, you have to take different, so there are many coupling constants, and you take slightly different limits and you arrive at the D0 matrix model in one case and the BFSS in the other case. But it's very similar to that, if you have seen BFSS.
And here, is it also Lorentzian time, like this?
Yeah. This is a Lorentzian. So this is like standard quantum mechanics. This is a real time.
Okay.
Yes. Thank you. Thank you for asking the question. Okay, so now I'll talk about target space entanglement. So to begin with, let me consider a simpler example. Is that let's consider the quantum mechanics of one particle moving in one dimension. And so in quantum mechanics, first of all, there is no space, but you can define entanglement in the target space, namely the space where your position operator takes value. So there's an operator which you can use to measure the location of this particle. And so the space that I've drawn is that space where the position operator takes its value. Let's say your region of interest is x greater than 0 in the target space. So the first thing you note is that the Hilbert space does not tensor factorize. Instead, it decomposes into a direct sum, not a direct product. Because if you have a wave function on the space, so the wave function can be written as something that's supported on x greater than 0 and something that's supported on x less than 0. So You see, that's the first difference. So then how does one define, reduced density matrix and so on? So let's say you start with a pure state. You can get to a reduced density matrix corresponding to this region of interest. But it takes the following form. It sort of separates into two blocks, if you will, into two sectors. And roughly these two sectors correspond to whether the particle is in your region A or not. So if it is in region A, then the density matrix essentially acts like it should. When it's not in region A, it acts trivially. So this is an identity, and this is some number, complex number, real number in fact. And so yeah, so the reduced density matrix takes this form. It separates into sectors, and once it separates into sector, it's easy to define the entanglement using the standard von Neumann formula. And in this example, you get a very simple formula as this, where PA is nothing but the probability of finding the particle in the region. So it's like minus PA log PA minus 1 minus PA log 1 minus PA, which is probability of finding the particle in the opposite region. In general, you can define target space entanglement even in field theories by imposing constraint in the target space where your fields take values and not where they live. What one does find is that the Hilbert space still does not tensor factorize, but it decomposes into a direct sum over tensor factors. So it has the following structure. So for example, if you have n identical particles, quantum mechanics of n identical particles, your Hilbert space will be a sum over different sectors, and the sectors are labeled by the number of particles in your region of interest. And within each sector, there is a tensor product. And what this allows you to define a density matrix and a reduced density matrix sector by sector. So reduced density matrix takes the following form. It takes like a block diagonal form where each block corresponds to a sector. And you can define reduced density matrix in each sector because you can do the standard tracing over a bar in a given sector. So this allows you to define the reduced density matrix. And then again, using the von Neumann formula, you can find the entropy in each sector and then sum over all sectors to get the full entanglement. So this is the structure of target space entanglement. Now let's come to the main interest of our talk, which is entanglement in the matrix photo mechanics in this model. So I've rewritten the action here. So suppose, let's say I choose one of the matrix. Let's say this is X1. And I ask, what is the entanglement of, let's say, this K cross K block, which is drawn in red, with the rest of the matrix? Immediately, this question does not make a lot of sense because the theory has gauge transformations. And then when you apply gauge transformations, the red elements will mix with the blue elements. That seems like it's not a good question. However, to motivate, let's say in the bulk, I'll sort of go between the bulk theory and the boundary quantum mechanics. Let's say you were interested in this region. X1 is one of the coordinates, and you're interested in this region where X1 is greater than some number D. So what we do is we look at the corresponding matrix X1. So this is the coordinate. This is the matrix. It's an n cross n matrix greater than D. So the first question you'll ask me, what does it mean that matrix is greater than D? To see what that means, you have to diagonalize the matrix. So you have these gauge transformations. You use that gauge transformation to diagonalize the matrix like X1. And there are some other residual symmetries like Y symmetry and so on, which is basically the permutation symmetry of the eigenvalue. You use all of that, you gauge fix, and you find, and then it makes total sense to ask what is the entanglement of this block, which is now basically corresponds to k number of eigenvalues with the rest. And since we are interested only in this, the eigenvalues which are in the region of interest labeled by this color A, you can integrate out the rest of them. This is for x1, which you can diagonalize, but there are 8 other matrices which will remain non-diagonal. You cannot diagonalize all of them at the same time. So the question is, how do you deal with them? And there are 2 versions for this. And the reason is the following. So the other matrices in general have all the 4 blocks. The first block we should keep. So remember that we have gauge fixed. So now there's no gauge freedom left, which will mix the red with the blue. So now when I say keep the red, it makes sense, because you want to keep the matrix elements in this block, but you want to integrate out the others, the blue blocks. So the wave function in general will be a function of these matrix elements. So you start with the density matrix and focus on a particular sector, which is labeled by K. You integrate out these other blocks. But there are 2 versions we propose. In the first version, you integrate out everything else, all the 3 blue blocks. In the second version, you only integrate out this small square block, n minus k cross n minus k, but you keep this block. We believe it's the first one that should be true, but we don't have a concrete calculation to say that it's the one. And the to understand that, what we are doing is you have to look at the physical picture. The physical picture is the following. So for now, as I said, the matrices do not commute, so you cannot diagonalize them. But suppose for a moment that you could diagonalize all of them. Then the eigenvalues correspond to the locations or coordinates of the 0 branes. If you could diagonalize all of them, then x1 of this 0 brane will be its location, the x2 will be its x2 coordinates, and so on. But in general, that's not true. And the off-diagonal elements, so for example, the off-diagonal elements in this block, in this red block, they correspond to open strings stretching between the 0 branes. So this is a physical picture. In general, if you have other blocks, so these blue blocks correspond to 0 branes which are outside your region. So let's say this line is x1 equal to b. The right-hand side is my region of interest, the left-hand side is not. So then these dots would correspond to the diagonal entries here. And if you have non-diagonal entries, they would correspond to a string stretching between these. So in the first version, we only keep the following. We only keep the red dots and the red strings. That was our first version. In the second version, we keep the red dots, the red strings, which correspond to these. But as we said, we also keep these 2 blocks, which correspond to strings stretching between the 0 brane in our region of interest to the outside.
I have a question on this D.
Sure. Yes.
Where this D appear? Like here, you choosing in the bulk, you choosing the x1 is greater than D.
Yeah.
But in the
so
matrix, like in previous
right.
Yeah.
So let me say. So this picture is actually in the bulk. So yes. This line is x1 equal to b, and this is the physical picture of what happens to the 0 branes.
Yeah.
So the constraint you impose. So this was a bulk region. We promoted it to this constraint.
Yeah.
And once you promote it to this, to impose this, you have to diagonalize x1. And once you do that, that's how the constraint comes.
You mean this is from the k1 to lambda 1 to lambda k, they are greater than D.
Oh, yeah, sorry. Maybe I forgot to mention this. So there is this while symmetry, which is basically the permutation symmetry. So you have to while order them. So you arrange them in a particular order. So I arrange them in a decreasing order. So lambda1 is greater than lambda2 greater than lambda, and so on. So the first k of them are greater than b. The rest are smaller.
Oh, I see. Okay.
Okay. So that's why this red block is the one I keep, and the others I throw. Thank you for asking that question. If it wasn't clear, yeah, I should have been more clear about that. And the other matrices, as I said, you again keep this block because they correspond to zero branes that are within your region A, and the rest you should integrate out. But it's not clear, so we propose two versions: one in which you only keep these eigenvalues and the open strings, and the other which you keep these also keep these off-diagonal strings. So it's not clear because some of the strings are extended objects and some part of it is in your region. So it's not clear whether you should keep them or throw them. So therefore we propose two different versions, one in which you keep them and one in which you integrate them. Okay, so now let's move on to bulk entanglement. So very quickly, I'll go back to the bulk geometry, but now I consider a slightly heated temperature. So when I initially wrote it, it was at 0 temperature. Here I consider it at a slightly higher non-zero temperature. So it's like a black hole in the 10 dimensions, and it has a horizon given by RH. The temperature is related to the horizon in such a fashion. And all this is still true, and the supergravity description is valid when the temperature is small, and so on. So in this geometry, I again choose this region. I choose an entangling surface given by x1 equal to d, and I'm only allowed to make measurements, let's say, low energy measurements in this region, x1 greater than d. You could, in principle, choose other regions. You can choose spherical regions, which we do in our second paper. But this is clearer and easier to handle. That's why we use a planar region, planar entangling surface. So this is the setting. You have some horizon. This is your entangling surface. To the right of it is your region of interest. And as I proposed in the introduction section, that the entropy must be the leading entropy in small g Newton expansion should be given by area by 4g Newton. So I have to calculate the area of this x1 equal to d entangling surface to get the entropy. So that's what I proceed to do. It's some formula. You have the metric. You can calculate the area. The first thing to note is that the area diverges, and therefore you think the entropy will diverge. And this is not surprising because this, the surface, entangling surface, is of infinite extent. So you choose a surface which is of infinite extent, so it was obvious that the area would diverge. So now what do? What you do is you take two slightly different geometries corresponding to slightly different temperatures. You calculate the area and take their difference. So when you do that, when you take the difference, this divergence that comes from the large radius part, that cancels and you get a finite answer. So I've written the final answer here, and I've written it in terms of I've written it in terms of the dimensionless quantities. So the quantities with the substitute 0 are dimensionless, and you get the final this answer. The first thing to note is that it's proportional to n square, which you would have expected. But remember that this answer should be somehow come from the boundary quantum mechanics. And it's reasonable because the boundary quantum mechanics has n square degrees of freedom. So it's possible to get an entropy which is of order n square. The second thing to note is that all all these quantities, D naught and T naught, they appear naturally in quantum in the boundary theory. So this answer one can in principle get from the boundary theory, and this B naught is just some number. It's, if you evaluate, it will be some 200 or something. So if instead of the Newton's constant, had you taken, let's say, for example, the string length as the cutoff. So when I calculated this, I used the formula that's area, and I used the cutoff to be G Newton, replace the cutoff to be G by G Newton. If instead, let's say I took something like this, where I calculate the area, but I divided by the string length to the power, with appropriate powers, I would see I will get an answer where the string coupling and so on keep on hanging. But such an answer you can never get from the boundary quantum mechanics, because the boundary theory does not know about the string coupling. It only knows about lambda. There's only one scale, and it knows about the temperature. It knows about the temperature if you put the theory on a finite temperature. So that's one more reason to believe that indeed it should be the Newton's constant that should be come into the entropy formula. So this is from the bulk side. So this is the bulk answer. Now we'll go back to the proposal, which you would have expected to be coming. I've already said that the bulk entanglement, the answer for area by G Newton from the boundary theory, is just given by target space entanglement. And the way to see it.
By the way, then how can you get the temperature?
In the quantum theory?
Yeah, in the quantum mechanics, like you start with the Lorentzian.
Yeah. So you put it on a normally you would put it on a cylinder. So it's like it has a real time, but it also has a periodicity in the Euclidean time. So that's how you get a temperature.
So you go to the Euclidean and calculate.
Yes.
Okay. Thank you.
Right, but I mean, if even if you have a temperature, you can still. It's easier to calculate things in Euclidean, true, but you can also do real-time calculations with a temperature. It is possible. It's not.
Yeah, it's possible.
It is possible.
That's true. Yeah.
But right, the first thing would be to just do the Euclidean calculation.
Okay.
Right. Yes, as I said, that this is our proposal, that given some constraint, if you have given some region, which you can always define in terms of some function of the coordinates greater than 0. Let's say this is your region A is defined by this constraint. All you have to do is pull that back, this relation, from the coordinates to the matrix. And once you do that, as was motivated by the physical picture, this constraint naturally leads to an entanglement in the quantum mechanics theory. And we propose that it's this entanglement that is dual to the entanglement in the bulk. I should mention that this is not obvious because, for example, I considered a linear constraint, which is x1 minus d greater than 0. In our second paper, we'll also consider this spherical constraint, which is sum over I xi square minus b square greater than 0. But if you have a non-linear constraint, let's say, for example, let's say you have x1 times x2 square times x3, or some such term, then there will be an ordering ambiguity when you go from the coordinates to the matrices. We believe that one should use a while ordering for that situation. It's not immediately clear, but it is also true that the difference between ordering one expects to be suppressed in 1 by n, if n is large. However, that issue still remains. But up to that issue, there's a precise mapping of a region in the bulk to a region in the target space. And then once you go to this region, you can define target space entanglement. And we have proposed that the bulk entanglement, which is expected to be proportional to the area, should be reproduced by target space. In particular, I should also mention again that we had two versions. I've only shown the X1 matrix here, but there were other matrices which are non-linear, and we proposed two versions from them. So for the first version, if you know the initial wave function or the initial density matrix, you can find the reduced density matrix by integrating out the other blue blocks in my picture. And you get a reduced density matrix sector by sector, and you can find the one norm in entropy and sum over all the sectors to get this answer. And our proposal is that this answer should agree with this answer. Now, there are examples where what I've said is actually true. For the 10-dimensional case, this D0 brane holography case, it's a conjecture, but then there are other examples where what I said is exactly true. So the first evidence comes from C=1 matrix model, which is dual to Dury non-critical string theory. And it was worked out by Sumit in mid-90s, actually, where he looked at this model. So this model has only one matrix, so you can always diagonalize it. And if you can always diagonalize it, then there are only n, then the problem is like n particles moving in a line. And you can then calculate the entanglement in two different ways. First is that you can second quantize that theory and have a field theory description and then calculate the entanglement. The second is you work in the target space itself using some methods, as it was done as recently, not very recently, but I think 3-4 years back by Hartnell and Messing, and you get the same answer. The familiar answer, the log answer for entanglement in one spatial dimension. The important thing to note here is that the epsilons, the cutoffs, are replaced by effective coupling of the theory. They are position dependent. And if you account for appropriate factors of n, you would identify it with Newton's constant in the dual string theory, the 2D string theory. So this is one example where the emergent space is exactly the target space, and therefore what we propose that bulk entanglement is target space entanglement is trivially true. So the second piece of evidence comes from a very recent paper. Actually, this came out I think 2 months back. It's also by Hartnell and his collaborators. In this example, there are two matrices. It's a two-matrix model. It comes from some Chern-Simons or quantum Hall physics. It's a matrix model with two matrices. This was with one matrices. What we have is 9 matrices. This is more non-trivial than this because it has two matrices. And the emergent space here is a disk. And one can consider circular regions in that disk, and as these people have done, and then you can calculate the entanglement in this model. And they indeed find an area at law. So they find entanglement which is proportional to the sun. It's 2 dimensions, and the entangling surface is a curve, so it's a line. They find that the entanglement is proportional to the perimeter of the line. And moreover, it's finite at finite end, which one should expect. So these are two examples which confirm that our proposal is indeed true. The reason that they were able to do this calculation was because wave functions are known in this model. In D0 brane quantum mechanics, for example, it's known that there is a bound state, but the wave function is not known. So so it's not possible to do analytic computations at least. But we hope that we could do numerical calculations. One more thing I should say is that while the geometry exists only a strong coupling in large N, the notion of target space entanglement continues to make sense at arbitrary coupling and arbitrary coupling. So maybe it continues to provide a definition of entanglement in theories of gravity. However, I must say it's not clear how to map in that case to geometry, because the geometry does not exist. But still, it's something we hope, something we can learn and say about in the future. I've already talked about the RT formula. The first difference is that in our theory, which is quantum mechanics, there are no RT surfaces. The second difference is that even if we consider a theory which had a spatial extent, in this entire talk, I discussed surfaces in the bulk which are not necessarily extreme. For example, I chose the plane, which was not an extremal surface, but RT surfaces are necessarily extremal. Moreover, if let's say your theory, so in this talk and to some extent in our paper also, we only focus on D0 planes, but there is in general Dp-brane holography for t equal to 1, t equal to 2 also exists. And we believe that such a notion is true there also. But there you have a new thing. And the new thing is that since the boundary theory also has a spatial direction, you can you can consider a region in the base space, but you can also consider a constraint in the target space at the same time. So it's like, so this more general notion will interpolate between the standard entanglement and the target space entanglement. And it would be very interesting to see what the bulk of such constraints correspond. How am I doing with time? This section is actually not.
Actually, there is not that sharp limit, so you can go ahead.
Okay, sure. So anyway, this is the last section before I summarize. So when I defined target space entanglement, the definition was based on the constraint, and I gauge fixed. It was not very clearly pretty, but there is a way to define entanglement in a gauge-invariant way, and so that is using.
Here, when you say gauge invariant, it's a UN gauge invariance of the quantum mechanics or some other gauge invariance in the bulk sense?
I mean quantum mechanics. So I mean entanglement is gauge invariant. That's why when what I mean by that is that a method which does not rely on fixing a gauge. You given a theory, you don't have to fix gauge. I mean, normally in a gauge theory, it's when you do calculations, you choose a gauge which is helpful for your calculation. But here I'm going to tell you about something which is more abstract. It's true in it allows you in principle to get entanglement without doing this gauge fixing and so on. So that's the kind of thing I'm going to talk about in this section. So there's a notion of entropy that one can define given an algebra. So an algebra is nothing but a set of operators, and the sum and product of those operators closes within each other. So for example, you can an example of an algebra is like a set of n-cross-n complex matrices. They form more formally an algebra is like a vector space with a product structure, with a product. So that this set of complex matrices is a vector space, and there is a product naturally, which is the matrix multiplication. So this is an example of an algebra. More generally, you can define algebra given a Hilbert space, because Hilbert space is also a vector space, and the algebra, the operators in that Hilbert space form an algebra. In particular, in such a case, there is a special operator, which for obvious reasons we call rho. It will be the density matrix, which has the following properties. It has the property that it satisfies the two properties. First, that the expectation value of all other operators in the algebra are given by this formula. The second is that it's normalized. So given these two properties, the density matrix is uniquely fixed. It's an operator, and the entropy of this algebra is just defined as the von Neumann entropy of this density matrix. So this is more formal, but you can see that already that it's equivalent to what we have been doing. There also we had, so this information is equivalent to knowing the state of your theory. But it's more formal and abstract. So the question we'll ask now, that is there some operator cell sub-algebra corresponding to a target space constraint? So we imposed a target space constraint, let's say x1 greater than d. That means we are only allowed to make measurements roughly in the region where x1 is greater than d. So that corresponds to a sub-algebra and of a sub-algebra. And the question is, can we find what that sub-algebra is? So, so first consider the example of single matrix. So if there's a single matrix, you can always diagonalize. And the typical one-body operator looks like the following. So this lambda are the eigenvalues. So it's like position. I is the ith number because there are n of them. I labels the number. Pi is the canonically conjugate momenta to lambda. And so this is a typical operator. Now to find such an algebra, what you have to do is first define a projection operator. The projection operator is the for the let's say your region of interest is some region A. It could be, let's say, x greater than 0. Then I define my projection operator as such. Now this delta function will only click if my eigenvalue lambda, which I measure, will be in region of interest. So this is how the projection operator acts. And it satisfies the standard properties you expect of a projection operator. Now, to get to sub-algebra, the operators relevant to this constraint, you simply project all the lambdas and the pi's with these projection operators. And I called it with the superscript p, and similarly for pi. And then starting with this operator, just replace all the fundamental lambda and the position and momentum by their projected forms, and that gives you the relevant operator. And the set of all such operators will be the operator algebra corresponding to that target space constraint. That was for example of one matrix. You can do this in general when you have all the 9 matrices. The projection operator has to be appropriately defined. It's defined like such. So you have some, remember that you can define a constraint by some function of the matrices. And you define the projection operator to be a delta function of x minus this. So it only clicks when the constraint is satisfied. And just as before, then you start with the fundamental matrices, and pi here is the conjugate momenta to x. So you start with that, you find it projected form. So you project it using this projection operator. Similarly, you do with the momenta operators, and starting with any operator which is, let's say, a product of these fundamental matrices, you can obtain the projected version, or rather the sub-algebra version, by projecting all of them individually and then taking the sum. It's notice that it's different from only multiplying the final product with the projecting the final product. You have to individually project each of the x's and y's and then again multiply. And this leads to the sub-algebra of operators relevant to the target space. So in principle, if So this is the sub-algebra for operators, which is formed by all the sums and products of such operators. If you know this, and you can, in principle, construct the density matrix using this by solving these equations, and then the von Neumann entropy gives you the target space entanglement. This is a formal, more formal definition. Most probably you will not use this when you are doing calculation. Yeah, yeah. So yeah, that's I've come to the end of my talk. I'll conclude by giving a summary. So we gave a precise definition of the target space entanglement in boundary theories. And while we only talked about quantum mechanics theory, quantum mechanics, you can generalize this to higher dimensional field theories. For example, to Dp-brane holography, with not just zero, with D1, D2 brane holography as well. And we proposed in our paper and here that within Dp-brane holography with p less than or equal to 2, the target space entanglement is provides the notion of entanglement in the bulk, which in the semi-classical limit should just be given by the area formula for any bulk region of interest. Now, I said that there are some hints, there are some examples, the C=1 matrix model, the quantum Hall matrix model. They do indeed verify our proposal, but a proposal in the full theory in our matrix model has not been done. And the reason for that is one does not really know the ground state of such a complicated quantum mechanics system. So most likely a direct test will have to be numerical. There are some open questions, in particularly, in fact, there are a lot of open questions. I've just written two. In the geometry that we consider, the zero-brane geometry, there are some extremal surfaces. And the question is that, are they in some case special? And there was a paper by Ramstein and collaborators which tried to say that the extremal surfaces must be somehow special because they're in some sense closer to an RT surface. But in our way of doing things, any surface, as long as you are working in semi-classical limit, all surfaces are equal. It's not that an extremal surface play any special. The second thing, and I think the more interesting thing to ask, is what can we say about bulk reconstruction? Is something like that true in this example? Let's say we focus on D0-brane holography, and we gave this map that somehow target space is related to this the bulk geometry. Then it should be possible that this sub-algebra of operators that I talked about, using them, it should be possible to construct operators in the bulk. It's not clear how one would do that because in the spirit of these papers, but it's not clear how to directly apply these to our setting, to the D0-brane holography. And it's related to this question, what sort of bulk measurements are accounted by the operator algebra. There are much more open questions, and there is also some continuing work, but I'll stop here. Thank you.
Yeah, thank you very much for the very nice talk.
Yeah,
and yeah, please ask question. Actually, I have several questions.
Sure.
Yeah. First of all, you have a fermion in your model.
Yeah.
So of course it does not give the background, but it's still, when you consider the calculate this entanglement, that fermion
in principle
contribute.
Yes.
In the bulk calculation. So I just wonder, because it's in the bulk, it's not, how is it geometric? Like in the dual bulk theory, the bulk entanglement is just calculated by classical geometry, is it? Or do you really calculate that? Then
then
maybe
yeah.
I see.
But you know, your question is still relevant, that the fermions are there. This is a supersymmetric field. So
Yeah,
fermions might play some role. It's not immediately clear to me, because
but the uh-huh.
the, you know, the geometry is in some sense encoded in these matrices, in these X matrices. Uh, yeah,
But maybe it gives the subreading, like this
yeah.
classical like a phase will be A over 4G Newton, but
Yes,
there will be
yes.
quantum fluctuation, maybe fermion
Yeah,
give
yeah,
that.
yeah. Perhaps at the next order and onwards, the fermions will become important. Yeah.
I see. So in your
Ah,
two paper, you completely ignored this fermions.
yeah, that's right. We only
And
talk about the leading
uh-huh.
answer. Yeah.
So in the bulk geometry, you can like consider the horizon at finite
Yeah,
temperature.
yeah.
How can you capture this horizon or the entanglement entropy of the black hole in the D-brane? Is it possible?
Yeah, so you just so for our calculations, sorry. Yeah, here it is. So I choose this surface, right? But let's say you choose the surface to be the horizon, this r equal to RH itself. And let's say you calculate the area, and that will agree with the, I mean, it has to agree because it is the Bekenstein-Hawking formula.
Yes,
And
that's right.
and my answer and our answer will be that you just follow what I said, apply it for this particular entanglement surface, and the answer you get from the target space should match this answer.
You mean you give the yeah, go ahead.
There is really no difference as such between special horizon, which is an extremal surface, or some plane you draw, which is not an extremal surface. Within our proposal, it might be important at, I think it might get important at higher temperatures, higher energies, or at subleading levels.
So you mean this horizon cannot be captured in your target space entanglement, or
no, it should be possible, no? But
I see.
The thing is that first of all, like, we haven't really done this calculation, so I don't know immediately what the answer should be.
Okay.
I mean, if there will be some hindrance in doing this, but it's not immediately obvious what that hindrance will be. But I suppose you could just do what I did for this surface. And as far as bulk is concerned, you can do this and you'll get an answer. In the boundary theory, the problem is that this map, which I showed you, this pull back from the coordinates to the matrices, this itself is not, it's actually, this is supposed to work precisely only at zero temperature. At higher and higher temperatures, this map will be modified in a temperature dependent way. And it's not known exactly how that will happen. But for small enough temperatures, and that is why in our calculation we took this limit that RH is small. In that limit, you can again have you can calculate the target space entanglement using that map from the bulk space to the target space. But the point is that this map itself might get modified at finite temperature. So yeah.
Okay. And what about this? Here you talk about the this entanglement entropy, but as you know, there are many other quantities like complex.
Yeah.
And the bulk, you can get calculate some bulk like I'm not sure. There in the
Yeah,
holography there is a
you're right. You're right. In
conjecture.
fact, I can consider any quantum information quantity and calculate it in the quantum mechanics theory. And we haven't thought about what will happen or what should happen for them, because it's true. You can, in the quantum mechanics theory, you can calculate whatever, any entropy, mutual information, any of these quantities. And it would be interesting to map them into the bulk and say something about the bulk. Yeah, that would be an interesting thing to do. We only focused on entanglement.
Yeah, in particular, like because in the bulk complexity, there is some proposal, at least in the holography, like action or volume. But in the target space, maybe it's because it's a matrix. There may be some way to define complexity. So I just wonder how.
My feeling is that when you define complexity, you'll have to define it in the space of wave functions. So, I mean, you have this matrix and you have some wave functions of these matrices. And complexity, you define, you choose initial state, you choose a target state, and complexity is defined as, the number of elementary steps it takes to go from one state to the other. So it's immediately not clear in this, in D-brane holography, it's immediately not clear to me that, it should correspond to some sort of volume or action. But it's a very interesting question. If there's something like that exists, then we should definitely try to understand.
Okay. So, and my last question is, so this kind of technique, can it be applied to the, like it's not the target, but anyway, this super usual like a holography, not only D-brane, but like a super Yang Mills and the other string. So is it possible?
So I think I don't I don't really know, but my guess would be, so usually in holographic theories, we only look at the ADS space, but the ADS space always comes with the product. Let's say ADS 5 cross S5 or ADS 3 cross S3 cross T4 or something like that. My guess is that if you consider a partition in the, let's say the sphere part, that should somehow be related to the target space entanglement, because it's the fiber direction. One will have to make this precise, but that's my expectation would be that regions in the sphere in the product space would correspond to some sort of target space entanglement. It's not very clear though, because we haven't really. Yeah, it's not immediately clear, but that's my guess.
Okay, thank you very much for the nice talk today.
Thank you.
Let me start the recording.